Good day, everyone. Let's start the session of this colloquium that is made to celebrate Professor Andrejs Cēbers' birthday and is named 50 years in the World of Magnetism. It will be mostly in English, but don't worry, I guess we can deal with this. It's a part of the 76th annual conference of the University of Latvia, and before we start, we are recording this and streaming it online so that people that can join here in this auditorium can watch it online. So please turn off the mobile phones, at least turn off the sound, and please try not to use Wi-Fi too much because it's streamed through Wi-Fi. Hence, if you overuse it, then people that watch it will be angry, and we don't want that. So without spending too much time on introduction, I think the first session will be a nice overview, and I will not spend the time of the speakers, so I will invite the first speaker. It's Elmārs Blūms from the Institute of Physics of the University of Latvia. Elmārs, lūdzu. Please.
I prepared my talk in English, but I would like to speak in Latvian, because he will be not many signs, but very many remember things for all times, and it will be more easier and more nice to speak in English than I can speak about some nuances also. Excuse me. Tā, vispirms mans uzstāšanās mērķis šodien nerunāt tik daudz par zinātni, bet runāt par vēsturi, par magnetisko šķidrumu pētījumu vēsturi Latvijā, un tas ir tiešām interesanti parādīt, tāpēc, ka mēs praktiski Latvijā piederam vieniem no pamatnicējiem šitiem pētījumu virzienam pasaulē. Un arī Andrejs, tūlīt jūs redzēsiet, Andrejs arī viens no tiem, kas praktiski sāk šos pētījumus no paša sākuma. Tā, vispirms šeit es pāris vārdos es parādīšu, kādas ir attīstības sākuma pētījumiem. Vispirms pirmie magnetisko pētījumu uzsākšanu daudzos gadījumos saistā Rozencveiga rakstu ferrohydrodynamics, kas bija publicēts Physics of Fluids 64. gadā. Pēc tam mēs iesaistījām pētījumos ar 67. gadu. Tad pētījums sāk augt, un šeit ir dažādi maksimumi publikāciju skaitā, un tie maksimumi saistāts ar Rīgas MHD konferencēm, jo jau no paša sākuma šī tematika bija iekļauta arī mūsu Rīgas MHD konferences tematika, un līdz ar to parādās to publikāciju pīki. Tagad, kā viss tas sākās? Sākās ar to, es beidzu 67. gadā kandidāti disertāciju, un mēs kopā ar mūsu kolēģi Mihailovu sākam gudot, ko dalīt tālāk. Un pēkšņi mēs izlasījām šo Rozencveiga publikāciju par ferrohidrodinamiku, un nospētām, ka tas ir ļoti interesants objekts, un sāksim strādāt. Man bija diezgan viegli pārslēgties uz pirmiem eksperimentiem, jo mēs strādājam ar elektrolītu, konvekcija elektrolītos, un viegli bija nomainīt elektrovadošos elektrolītus pret paramagnetiskiem. Un pirmie mūsu darbi saistīti ar to, ka mēs parādījām, cik spēcīgi var būt termomagnetiskā konvekcija, kas var būt pat elektrolītos, var būt spēcīgāk par tas ir gravitācijas stabilitāte. Un tad 68. gadā Fizikas institūtā nodibinājām speciālu laboratoriju priekšām pētījumu, man nozīmē par laboratorijas vadītāju, un sākumā bijām es, Mihailovs, tad Ozols ļoti labs teorētiķis sagatavos mūsu universitāte bija, un tad iesaistījās divi doktoranti, vien Moskvojs un Fēģins. Mazgovais sāk mēģināt atrast magnetiskos kolēģis un pēdējais turpināja uz konvekcijas pētījums ar optiskām metodiem. Īsti pētījums sāk izvērsties ar 1971. gadu, kad laboratorija atnāca no universitātes mūsu beigšies ļoti talantīgie studenti Cēbers un Majorovs. Cēberi jūs ziniet, viņš ir profesors universitāte, Majorovs joprojām mūsu laboratorijā strādā Salaspilī, vēl joprojām aktīvi darbojās. Tad tā, par galveniem rezultātiem, kas ir, es runāju par periodu līdz 1993. gadam. Tā laikā ir sagatavots, man arī vieglāk būs, labāk pats redz, padomi kandidātu disertāciju vai padomu kandidātu disertācijas 10, aizstāvēts Rīgā, Maskavā, Jēngridā, Minskā, un tad padomu doktora disertācijas, lielās disertācijas 2, Rīgā un Maskavā. Un Latvijas jau republikas doktori ir, pie mums ir viens laboratorija, un franču doktors arī viens. Es runāju par to, kas ir mūsu laboratorija, nerunāju par to, kas notiek par profesors Cēbera vadībā šeit fakultātī. Un tad, kas pamazām sāk attīstīties arī, tas ir sadarbība, kontakti. Vispirms sāk piedalīties starptautiskās konferences no 80. gada, un sākot ar 96. gadu, 86. gadu, dažādās starptautiskās organizācijas, kas saistītas ar magnetiskiem šķidrumiem. Un īsti tāda sadarbība, tā sākās ar 90. gadu. Nākošais, es gribēju pāris vārdos par galvenajiem rezultātiem. Es sadalīju tādos vairākos blokos. Pirmais bloks ir fundamentālā pētījuma, un šeit es gribētu atminēt divus rezultātus. Viens rezultāts Andrejs ar Majoru iesāk, bet vēlāk ļoti ilgi vēl pats strādāja pie laborāta testnes, visdažādākos izpauses metodas un visdažādi nesapīšķušās veidi. Tas ir viens tās komplekss, ko mēs sacībāt. Un otrs ir mazliet ne tik plaši zināms, bet manā pusē nemazāk interesants, ir tas augtā magneto difūzijas izsaukta konvekcija. Mums izdevās viņu vispirms izvirzīt ideju, pēc tam iegūt hologrāfiskas koncentrācijas profils koloidos un salīdzinot ar teorētiskiem risinājumiem, tad blakus ir eksperiments ar teoriju, un teorija ir kalkulācijas ir izdarīts gadījumā, kad tiek ņemt vērā ne tikai kolektīvu difūzija, bet arī konvekcija, kas rodās tādā rezultātā, kad koncentrācijas frontes nav perpendikulāri magnetiskā spēka līnijām. Šī konvekcija var būt ārkārtīgi intensīva, un principā viņi var spēlēt ļoti lielu lomu arī magnetisko šķidrumu pielietojumos. Diemžēl pēc tam mums nav izdevies šo konvekciju tālāk pētīt dažādiem iemeslu dēļ, un pasaulē viņš pagājis, ka kaut kā tas efekti sevišķi pazīstams, un es gribētu, ja gadījumā izdosies iespēja pie šiem jautājumiem atgriezties. Tagad nākošais ir jau tehnoloģiski rakstura pētījumi par sevišķi temperatūru jūtīgiem magnetiskiem šķidrumiem, kur būtu izlietojumi dažādām pielietojumās, kur vajag izmantot magnetisko konvekciju. Dažādas automātiskas dzēšanas sistēmas tā tālāk, skaļu un dzēšanu tā tālāk. Tas ir otrs komplekss. Nākošais un šim kompleksam praktiski turpinājums ir ļoti liels darbs, ko veids mēs kopā ar radiorūpnes radiotehniku, kad mēs izstrādājam magnetisko šķidrumu tehnoloģiju un jau gandrīz sākam pielietot magnetisko šķidrumus līdz esēs skaidrums. Bija izveidot tāda akustiskā sistēma AS100, varbūt jūs atcerieties, un tur vidējā toņu skaņums tika tas magnetiskais šķidrumi. Diemžēl tas ir ļoti katastrofāli beidzās, jo te darbi beidzās 90. gadā, kad viss sabruka. Radiorūpnīca tiek iznīcināta, viss iekārtas izvērst uz Padomu Savienību, mūsu piloti iekārta tik vienkārši sadalūsīt rupi. Viņi gribēja paņemt no mūsu tehnoloģijas. Paldies Dievam, tehnoloģijas tika noslēptas, tehnoloģijas uz Maskavu izvestas netika. Bet, principā, tas darbs beidzās ar neko ārkārtīgi lielu ieguldījumu pūles, principā būtu ļoti labi skanējis Latviju pasaulē, un tas viss beidzās ar Latvijas radiorūpniecības sabrukumu. Tad nākošais arī ļoti interesants kompleks, kur, diemžēl, viņš labi iesākās, bet neatrada turpinājumu, un neatrada turpinājumu tāpēc, ka tajā laikā Latvijā bija attīstītas fundamentālās fizikas zinātnes, bet nebija fundamentālas medicīnas tajā laikā. Tajā laikā praktiski visi mediķi bija praktiskie mediķi, un ja vajadzēja kaut kādu sadarbību, tā gāja ar praktiskiem mediķiem, un, protams, tādā veidā nevis izdarīt nevar. Vēl galvenais, kas ir? Mēs veicām pētījumus par masīvas magnetisko separāciju, hemoglīnus ar dažādās modifikācijās, magnetisko separāciju. Un devām priekšlikums, kā var izmantot gan diagnostikai, tas ir magnetiskās gribšanas reakcijas, varēja noteikt hemoglobīnu formu, teiksim, metahemoglobīns pie malārijas ir ļoti stingri izteikt. Paramagnetisks to ļoti ērti ir atrast ar magnetiskām metodēm. Tālāk, mēs gājām vēl tālāk, mēs iegūm tā saucamās magnetiskos elektrītus. Teiksim, izpumpēja no hemoglobīna ārā un membrānās iepludināja magnetiskās daļiņas, viņš un izmantoja to kāda depo priekš zāļu transportu. Tas arī mums ir patents pat, bet viņš beidzās arī 90. gadu, un tagad parādās ārzemju konferences, parādās darbs tādā pašā virzienā, mums, protams, necitē. Te sadarbība bija mums ar Javarkovska, un tad mums bija arī institūta sadarbība. Bet sadarbība bija arī ar Maskavu, jo daudz eksperiments var izdarīt labi Maskavā. Mums bija viens aspirants no Baka institūta Maskavā, un viņam bija kontakta Čāzava institūta, un tur mēs veicām pētījumus par magnetisko preparātu. Tas ir preparātu magnetisko lokalizāciju. Šeit ir 2 eksperimenti ar neiroparātiskiem preparātiem. Ir redzams, ka viena kāja augšējās līknes ir, kur ir reakcija uz muskuļu aktivitāti. Ir prova un apakšā, kur dziļākās līknes, tās ir uz tās kājas sunītiem, kur tika uzlikt magnetiskais lauks. Efekts diezgan. Šie pētījumi, viņus varēja arī turpināt, bet viņi ar 90. gadu pārtrūka, un varbūt, ka pareizi ir pārtrūka, bet tikai vēlāk mēs uzzinājām, ka tas projekts ir bijis ļoti nepatīkams. Tas ir bijis ar neiroparalītiķiem, projekts, un māc, teiksim, arī karaspēku paralizēšanai. Paldies Dievam, ka mēs no tā projekta tikām vēlāk ārā. Tā kā tev vispār darbs ļoti interesanti. Tagad šitie pētījumi notiek atsevišķi konferences, bet tur mums vairs pārstāvot neesam klāt, jo mums vienkārši spēku vairs tam. Viss tas turpinās pasaulē. Tā, un tagad es pāriešu jau pie mazliet pie tādām sadzīves kaut kā vietā. Šeit ir mūsu kolektīvs, laboratorijas 87. gadā. Tas ir gandrīz tajā laikā, kad mēs sasniedzām kulmināciju. Mēs bijām ieguvuši papildus līdzekļus no Maskavas ļoti liels. Mums principā bija lielākā laboratorija institūtā. Šeit nav redzams es, jo es pats uzņēmu bildes, bet te ir redzam daži mūsu cienījumākais mūsu teorētis Roberts. Centrā bildē, un tur aizmugurē ir Andrejs Cēbers redzams. Tā, tagad laboratorijas smadzenes, kā saka. Šeit ir mūsu teorētika grupa. Pirmais ir Aleksandrs Čukrovs, viņš ir Latvijas students, bet viņš beidz un pētījums Maskavā. Aizmugurē Roberts, ļoti spēcīgs teorētikas. Vidējā Andrejs, ja mums vēl, un tagad 40. Glasovs. Nākošā laboratorija daži kolēģi, Ērglis Clemson strādā pie koloida, magnetiskiem koloidiem, Lilija Matkevičs strādā ar šiem medicīniskiem jautājumiem, šeit ir Aivars Rimša, ļoti labs eksperiments hologrāfijā taisīt, un šeit ir, ja viņš ar lauvu veic eksperiments asaras separācijā, un šeit ir Majorovs arī bija Viņi man eksperimenti magnetoteroloģijā. Tagad par starptautiskiem kontaktiem. Vispirms, jau es minēju, kaut kā Rīgā notiek MHD konferences un savienības mēroga. Pirmās bija tās apsos Bļosas konferences, tas ir Volviks rasto. Mums visiem Latvijā ļoti patīkams atmiņas ir ļoti jauki pavadīt laiku, ne tikai zinātnē, bet arī sadzīviski. Un pirmais mēģinājums iziet starptautiskā mērogā bija 1980. gadā. Mēs mēģinājām Rīgā taisīt starptautisku simpoziju. Šeit ļoti augstā līmenī akadēmiķis sadalījums atklāja šo konferenci, bet mēs principā cietām neveiksmi, jo tas bija tajā gadā, kad Padomu Savienība iebruka Afganistanā un principā boikotēja, ne tikai sportiski boikotēja olimpiskās spēles, bet visi iesboikotēja arī zinātnieki. Mums atbalsta tikai 3 vai 4 cilvēki. Līdz ar to tas neko daudz neizdevās, bet toties man sākās ļoti negaidīts pavērsiet. Pilnīgi negaidīt man uzaicināja uz otro starptautisko hidrokonferenci Orlando, Amerikā, un tur īstenībā sev iepazīties ar ļoti daudziem nākošiem kolēģiem. Es kaut tā ar Dr. Rozunsvēju, tur vēl daži kolēģi, bet nav laika pēc par to stāstīt. Tad man uzaicināja arī uz trešo konferenci starptautisko, kas notika Bangorā, Karalistē. Jūs redziet, ka dalībnieku skaits nav sevišķi liels, bet tūlīt nāks lūzums. Tagad ir 86. gadā ir 4. konferences Japānā, kur arī jūs redzēt, dalībnieki ir diezgan daudz, bet ne sevišķi daudz. Un tad nāk lūzums. 88. gadā aprīlī, 27. aprīlī uzņēmums atbrauc pie mums Rotational, viņš uzprasījās uz Vidību institūtā. Mēs pavadījām divas ļoti intensīvas dienas. Vienu dienu lasīja lekcijas viņš, un otru dienu visi laboratorijas kolēģi lasīja savus ziņojumus par saviem pētījumiem. Mums izveidojās ļoti labā attiecības, un ar Ronu mēs esam personīgi draugi kopš seniem laikiem, līdz pat tagadiem laikiem, kad mēs abiem esam praktiski pēdējie. Uzņēmums atceros ļoti labi. 6. aprīļa, tas bija tajā dienā, kad notika sprādziens Mēs neko nezinājām līdz maiju sākumam, bet Rons man pačukstēja, ka viņš naktī klausījās Amerikas balsi Andrejs, kad ir notikusi avārija. Tāpēc atcerētu. Tagad pēc tam izrādās, ka viņš bija braucis pie mums, lai pēc inspekcijas procedūra, pēc tam bija pieņemts lēmums, ka 5. starptautisko konferenci taisāmies Rīgā. Jūs redzēt, cik plaši viņi bija. Tas bija vienkārši kulminācijas punkts ļoti daudzos gadu pētījumiem, jo šeit sanāca kopā viens pirmo reizi atklāti satikās padomu blokā un ārzemju zinātnieki bija nogrūši jebkuriku aizliegumu. Neviens vairs neņēma vērā nekāds liegums, notika viss ārkārtīgi ļoti augstu paceltā līmenī, kad zinātniskais līmenis ir augsts, kad ir ārkārtīgi augsts kolēģiālais līmenis, viss aizkārt, visi uz uzrādi sākot redz. Nākošā, un tad šeit jau sākās arī starptautiskie kontakti tehnoloģiskās lomās. Es tiku uzaicināts iezoties galvenajā ferrofluidiku kompānijā Ferrofluidiks. Šeit tas ir vēl pārējais lejā, bet redziet, kā tur ir padomu savienības kopā ar Latvijas tas ir 90. gads. Un šeit parādījās priekšlikumi par to, ka ir organizēta Rīga uz mūsu institūta bāzes organizēta Ferrofluidikas filiāli, kas apkalpot, austrumu bloku valsts. Protams, no tā nekas neiznāca, jo tajā laikā mums vēl nebija ne valūtas, ne pieredzes biznesā, ka tā principā viņi mazliet pasūta tā lieta. Toties, kas attīstījās, mūsu magnetoteroloģijas metodi ieinicējušos amerikāņu kolēģis, un mēs sākām sadarboties neoficiāli mērījumi metodikās. Nākošā konference bija 92. gadā Parīzē. Viņi jau bija diezgan plaši, tagad jau visi bija pazīstami. Viņi bija ļoti lietiši un ļoti labi organizēts konferences. Jā, par to laiku pirms tam, 89. gadā, es biju uzaicināts uz Parīzi. Mēs runājām gan par šo Parīzes konferenci, ka šeit izskatījās arī ideja par Latvijas un Francijas sadarbību doktorāta augstnāšu. To, ko tagad mums fakultāte ļoti labs ir, iesākums 1989. Gadā. Pirmo līgumu mēs noslēdzām 91. gadā, sāka realizēties viņš ar 93. un pamazām pārņēma to profesors Cēbers, viņš to programmu turpina šeit. Un tur nevar viss izšķirt, bet tur ir viss mūsu vecie franču kolēģi. Tagad beidzamais projekts, kas šajā periodā, padomu periodu noslēdzos, tas bija darbs pie lielas rokas grāmatas Magnetic Fluid Adaptations Handbook. Mēs sākām Parīzē 91. gadā, un ļoti grūts projekts bija, un nobeidzām tikai 96. gadā. Šeit ļoti liels autoru kolektīvs, un es biju iesaistīts arī tajā redaktoru padomē, šeit no redaktoru padomes Parīzē. Tagad nobeidzot savu to mazliet īso, haotisko uzrunu, es gribēju izteikties pateicību veciem un esošiem kolēģiem. Jūs redziet, viena jau vairs nav, viena ir emigrējusi uz Ameriku, uz Austrāliju, bet tomēr gandrīz puses ir saglabājušies zinātnē. Viena daļa ir universitātē, pats pirmais ir Andrejs Cēbers profesors, kurš ļoti veiksmīgi tur ir pētīts, kolēģi Josmā jau mazliet zinātnē plāksni. Tāpat ir arī fizikas institūta palikuši vieni. Visiem tiem veciem kolēģiem ļoti paldies. Paldies par uzmanību. Tā mazliet paldies.
Thank you, Professor Blūms, for the presentation. I think we're running a bit over the schedule, so let's keep the questions for the coffee break. Paturēsim jautājumus kafijas pauzē. Paldies. Let's thank again. And next speaker is from the University of Pennsylvania. It's Paul Janmey. Please, he will tell a bit about magnetic particles and how they go together with polymer networks.
Man būs taisn otrādi jādara, jo es tur tālāk runās angliski, jo es zinātnisku žargonu tikai varu angļu valodā pateikt. So I'd like to tell you a few things about our attempts, largely motivated by work with the lab of Cēbers, to try to incorporate magnetic particles into the kind of biophysical experiments that many people are increasingly doing. So I want to tell you 4 short stories. One is to give you a little background of the use of magnetic objects to look at biology, because it's quite long and sort of interesting, and not just biology, but soft matter in general. And I want to show you a couple of examples of that, and especially to the importance of applying both micron and nanoscale particles in magnetic fields that could either be put in large field gradients or rotated to put different geometries of stress on the molecules or cells and biological materials. And a couple of examples from our lab have been to either apply these particles to specific receptors on the cell surface, pull on them and see the cellular response, or to take slightly larger particles and put them into tissues and put local forces in a still physiologically functioning organ. And I want to finish with one very recent experiment that has been to attach nanoparticles to polymer networks, because we have a very nice result and absolutely no understanding of it. So Andrejs and his colleagues have a lot to work on. So here's the kind of motivation, the biological motivation for why increasingly people are interested in putting forces on cells and objects. And that is because in many clinically important contexts, in this case, the development of fibrosis in the liver from intoxication. It's an experiment in which rats have been intoxicated with carbon tetrachloride, and they will develop a fibrotic liver. But diagnosing and treating the early stages of this is still kind of obscure. And so one of the things with my colleague Rebecca Wells at Penn that we noticed is that if you induce at day 0 this chemical injury and then measure the shear modulus, the stiffness of the liver, that's in the black line, or the histological appearance of the cells and the matrix in the tissue, we send these samples to a histologist in the clinic and ask them, does this look normal or not? It turns out that the stiffness of the liver increases before you can see any pathology. But the pathology will inevitably arise, and we think it happens because the stiffening causes the cells in the tissue to misfunction or to malfunction. And we can show this in the laboratory by taking one of the cell types from the liver that is changed during fibrotic disease and simply culture it ex vivo on materials of different stiffness. So as if we put a cell on a very soft matrix with an elastic modulus about that of a normal liver, it remains unactivated. It stores lipid-soluble vitamins. It does what the cell ordinarily does. But if we change the material properties underneath it and force the cell to attach to stiffer and stiffer objects, as it does in the liver, and by doing so puts forces or meets larger resistance to its contractile energy, the cell spontaneously activates and does the biochemical processes that happen in a fibrotic liver. So we think that force or stiffness or something related to a physical property is driving the clinical pathology. And not only do cells respond chemically, but they also alter their own stiffness. So the mechanical properties of a cell are not entirely genetically encoded. They are very adaptable to their surroundings. So if you look at a stem cell taken from bone marrow and look at its stiffness as a function of the stiffness of the material that it sits on, it can change its own stiffness by almost an order of magnitude and predispose these cell types to differentiate into either cell types characteristic of very soft materials like fat, or cell types that are characteristic of stiffer materials. Okay, so these kinds of things have motivated people to try to understand how the cell measures or responds to forces. And from a molecular point of view, the way that the cell does it isn't really soft matter physics. It's not like a continuous drop wetting a surface. It's a little bit more molecularly oriented in that the connection between a cell, this round object of a cell, it's stuck on, it's making physical contact with its neighboring cells and with a matrix underneath it, and it does so by specific molecules at the transmembrane complexes that are linked to the extracellular world and then into the intracellular world. And one thing that biologists have been very interested in is if we can attach an object, a particle, to a specific one of these many, many receptors that are on the cell surface and pull on only that receptor, what will happen? Is that enough to change a cell feature? And also, if we can apply force to these objects, we can measure the stiffness of the cell. And the force measurements that are currently used are very largely based on indenting the surface of a cell, either with a needle or an atomic force microscope. And these kinds of deformations are usually just compressive. But increasingly, very often, people have attached magnetic particles to the cell surface. And these particles can be coated with a very wide variety of chemicals that can attach them to specific complexes on the cell surface. And then you could apply either a macroscopic field or increasingly with these little needle electromagnets, a large field gradient and then pull on the cell. Or you can magnetize the particle, put it in a magnetic field and rotate the field to put a twisting force on these cells. And by looking at the response of the cell, you can measure the elastic and the viscous character of the cell, but more importantly, you can put on an almost single molecule scale a specific force to a part of the cell membrane and watch the cell react. So this is a very old technology, and I think this is the first example in which people have done something like this. It's a really interesting collaboration between a guy named William Seifritz, who's an American botanist who went to work with Herbert Freundlich, who is a colloid physical chemist in Berlin. And in the early 1920s, they made one of these electromagnets with a very sharp tip. They put a piece of magnetite inside a cell, and they moved the particle around, turned the magnet on and off, and watched the particle respond. And this is actually one of the very first measurements of cytoplasmic viscosity, and they knew all sorts of things. They knew it was a non-Newtonian fluid. They knew there was some kind of elastic as well as viscous response, but they didn't know anything about the chemistry. And actually, if some of you are interested, this guy made a really interesting video in the 1950s describing some of this work, which is still on YouTube. So, and also, as you know, this technology was taken up by Francis Crick, famous for DNA, but that's not what he did as a PhD student. What he did as a PhD student was put magnetic particles inside animal cells and do basically the same experiment that Seyfried had done 30 years earlier. But the difference is he put an elliptical magnet inside a cell. So he didn't have to know the strength of the field gradient, he just had to know the strength of the magnetic field, and by rotating the magnetic field with respect to the long axis of the magnet, he could watch the displacement of a particle. So here's one of the examples from this paper from 1949. You turn on a field, the magnet rotates, you turn off the field, and it comes back. And so from this you can see that the cytoplasm is elastic and not just viscous. And they concluded many things, including the first measurement of the elastic constant, which is much lower than what people measure now, but still the basic idea is the same. So now these experiments can be done in a slightly more complicated way. Here's one example in a collaboration of ours with Chris McCulloch's lab at the University of Toronto. Instead of just taking a piece of magnetite, you can make a very small bead coated with a specific protein that allows you to attach that protein to a specified transmembrane, attach the magnetic particle to a specified transmembrane protein, in this case a class of proteins called integrins that link the outside world through the cell membrane to the cytoskeleton inside. And what we did with McCulloch is put different amounts of forces by putting a large electromagnet and putting a field gradient to pull up on this molecule and look at the cell response. And what happens when you pull on these things is the force is distributed partly in the cell membrane, and partly that activates stretch-activated ion channels in the lipid bilayer, but also it is transmitted into the cell through the cytoskeleton. And the more you pull on this object, on this transmembrane protein, the more the cell assembles its cytoskeleton. And you can look at biochemical consequences of this and morphological consequences of this. I hope this EM is visible. Here's where the bead used to be, and here's the cell underneath the bead. In this case, force was applied to the bead. In this case, force was not applied. I'm not sure if it's visible, but there are many, many actin cytoskeletal fibers underneath the place where the bead was pulled with a magnetic field, but not so much underneath a bead that is attached but not pulled on. And also the cell assembles these large bundles of actin fibers only if you put a force on the bead. If it's just chemically attached, nothing happens. And McCulloch and we have used this material, this method. You can isolate these beads and now do proteomics or Western blots and see which proteins have been recruited to the bead that has been pulled on. And by doing so, we can identify certain proteins like filament A that do not co-localize with the bead if you don't pull on it, but as soon as you pull on it, it gets recruited to that state as part of the process that the cell uses to respond to force. In a slightly larger scale, you can do this almost in vivo, and it's an experiment with my colleague Tyler Miller at the University of Texas, in which we've been studying the stiffness of the glomerulus, the part of your kidney that filters waste from the urine into the blood, or other way around, from the blood into the urine. And so this is a material that also changes its stiffness during diseases, and we'd like to be able to measure this and understand it. So the way this is done, this is a kind of the schematic geometry of the glomerulus. It's a topologically horribly complicated object, but these circles are small blood capillaries that are surrounded by a matrix and cells outside of which are urine. And by trapping magnetic beads, we can do the same trick. We can put a field gradient on there and measure the stiffness either of the intact particle or of this the same object when it's decellularized. And I leave you with one last puzzling thing. So we've taken this one step further in the last couple of years with largely with the beautiful particles that are made by Oksana Petrichenko, and we've done a lot of this with Costas Ērglis and other members of Cēbers' lab, in which we've taken these magnetic nanoparticles and coupled them to filaments. In this case, these are magnetic particles that are lining a PF1 virus, but we can also couple them into polymers in one of these networks. In this case, it's a fiber network, the network from blood clots. But the particles are attached inside of these fibers. And then we do the same experiment with a polymer network that we do with cells. We apply a field to these particles, quite a large field, and a beautiful rheometer that you have here in the Institute. You apply 1 Tesla field to this polymer network that has magnetic particles, and the stiffness, the shear modulus of this network beautifully and gradually decreases, and it decreases a lot. You turn the field off, it comes back. You turn the field on again, it gets softer again. So we can reversibly tune the mechanics of this network up and down by putting these fields on. We have no understanding what's going on. We don't know what's happening to the filaments or what the physics behind it is, but the result seems quite large, and it seems worth studying some more. So we conclude the magnetic particles have a lot on the scale of nanometers to microns, have a lot of uses that are only beginning to be explored in biology, and especially the ability to chemically modify their surface gives us a lot of new tools, and that incorporating these objects into biopolymers has the potential for making a lot of adaptive materials and to try to understand the physics of these soft objects. And finally, I just want to thank Andrejs and his lab for many years of coming here and playing around. Thanks a lot for your attention.
Thank you, Paul, for the talk. We have time for 1, 2 quick questions, please. Anyone? You're not ready to ask questions. Oh yeah, there is one, please.
First of all, thank you very much. I'm not a physicist, but I'm a medical doctor. But that's what I've seen, and I would continue, I guess, in my presentation that, you know, it's so always connecting with medicine and with biology. And for me, it would be really interesting how you're actually looking on hypothesis when you are starting to do something like this, because there is about omics and other things, and which is so important, and also it's in so, but basically you are working in physics, and how you are actually, when you are going for some hypothesis, what is your plan, how you to think, why you do one or other thing.
Oh, which particular condition or others?
That's what we actually, I also to see from previous speakers that sometimes it's quite difficult if you even collaborate with some practical physicians, but you also showed us very interesting things about kidney and other things, and how you are actually getting this.
So I think some of the motivation comes from things that physicians already do. So diagnosis by palpation. The reason that works is because you feel, and you even know about yourself that if you have something that feels wrong, there's something medically going on. But the reason it feels wrong is the viscoelastic properties of that tissue has changed. And I think for a long time people thought that the mechanical change was just a consequence of the disease. And so we and others have started to look at whether the physical change could actually drive the disease. And that seems to be increasingly commonly seen. But I guess the more specific question, how do you choose what to work on? I think it's largely accidental. Not all physicists, I think many physicians think that physics is just, not useful to them or anyone else. Yeah, but some are not, and so it's important to find those people. But increasingly, there's much more of it, and especially not only in diagnostics. It's the whole basis for using magnetic resonance elastography as a diagnostic tool. It's because the physical properties work, and there's an enormous drive for that, more in Europe than in the U.S. But I think that's it's largely accidental. It's what people who are interested in the same thing.
So I guess we should move on, so let's thank Professor Janmey. And the next speaker is from Clemson University, Professor Kornev, and he will talk about magnetic rotational spectroscopy. Here we go. Step towards back and the laser.
Okay. It's a great pleasure to be here and I'll talk about one piece of work we've done at Clemson and keep doing that, and I was trying to find some common points of interest to talk about this and share with you the excitement I have. And this is the third generation of students working on the things we call the magnetic rotational spectroscopy. And in a second I will explain you what it is. And just going back to spectroscopy, this is the light spectroscopy. Our interaction with Andrejs Cēbers. In the era of no cell phones, I don't have photographs from that time, but I do have some memorable pictures to share. So this is the first time Andrejs was very excited about making a theory of Kirchhoff rods, and he was discussing this on the Mechanics Congress in Warsaw. And we met there, and this is my little girl now. She's grown up, and we were thinking that I just moved to New Jersey. Then I moved to Clemson and invited Andrejs to talk about the development of that theory and the progress. And you don't see it. He was talking about the change of magnetic particles and some swimmers. Then we met next time, and he started looking in the bacteria. So in Rostock, he was talking about this, just starting very exciting things with bacteria. And then recently we invited Andrejs to talk about the recent progress of his group in the University of Georgia. And between these meetings, he also studied the fluid mechanics of waterfalls in South Carolina. Now, Paul already introduced you to rheology, so the focus here is a little bit different now. The problem with rheology, if you look at the materials properties of complex fluid, is that if you have the available instrument, the stresses and the torques applied, the disc, for example, are huge. So we are talking about millinewtons times meters, and if you compare the real shear stresses, the torques, which, for example, cells would exert on the probe, or here is an example of the worm, you will see that the torques are actually 9 orders of magnitude smaller. How to address that problem? Really, what do we measure when we apply this technology to analyze materials properties? And we have very many problems similar in insect, but also this is not just a fan, but if you are working with materials, especially in salt gel processing of ceramics materials, very thin films, you will also face the same problem of characterization of very thin films. And the simplest method, in my opinion, and quite reliable and robust, is to look at the reaction of magnetic rods on the applied magnetic field. But the history of that method is dating back to about beginning of last century. But the important thing now is the development of microscopy. It's easy to observe and track the full rotation of nanorods. So that allows you to do many things and probe not only small deformation, but also quite developed deformation and the stress. So what we have, the basic schematic, is that you put magnetic stage, and I was pleased to see that your lab is developing this kind of instrument, and you've put the liquid in question between two optical slides and embed the nanorods and force them to rotate. And watch on your computer what is happening. And the idea, I think this is what I know, probably you know more than me. Cvetkov was the first to actually introduce that idea of rotating magnetic particles. He was working on liquid crystals and applied magnetic field. Liquid crystals are typically diamagnetic, so he applied magnetic field to rotate and look at the phase transition of those crystals. And Frankel set up very nice theory for that, very simple and comprehensive. Then Paul already mentioned the next milestone in the development of magnetic rotational spectroscopy by Crick and Hughes, but they looked at the relaxation of magnetic material after pulsing with magnetic field. Then I think now the attraction of magnetic materials, magnetic particles to characterize complex fluids was quite drawing, and there was a big expertise developed in magnetic fluids. So, and Andrejs and his group were probably the first to look carefully and lay out the theory how to look at the instabilities associated with rotating magnetic rods, magnetic filaments, and liquid droplets. But I think Bach-Crick group were probably the first to take advantage of that knowledge and look at the materials properties of the object, considering the magnetic particles as probes. So in this example, I think they will look at the small deformation of the material upon application of magnetic field. So at one visit, Andrejs visit, we've talked about this, and my wife at that time was a graduate student in Drexel University. She's a chemist, and she was stuffing carbon nanotubes with magnetic particles, and we were challenged to characterize magnetic properties of those particles. So, and we suggested to look at the rotation, and when you look at magnetic nanotubes, difficult to observe, but you can take advantage, as I said, of the full rotation and look at the dark field microscopy, so you can see about 50 nanometers nanotubes in a microscope. So it's a very straightforward way to analyze that, and we look at that, and Andrei was very excited. Because he was excited, he was an expert, and everybody were happy. So I considers that was a big step forward, so I kept looking at that, moving to Clemson. And recently, his work, his theory on analysis of the rod rotation in complex fluids also put forward a lot of other works around the world to probe complex fluids, especially considering them from the point of view as Maxwell or Kelvin materials. So why magnetic rotational spectroscopy? Why we call it? Because now if you look at the balance of forces acting on the rotating magnetic rods, so the driving force and magnetic force, which is balanced by the viscous friction. So, and if the rod is rotating, and that viscous friction is associated in a simple Newtonian fluid, is associated with viscosity. So, measuring the drag coefficient and identifying that drag coefficient with the shape of the rod in particular, considering it as a cylinder, you can extract viscosity directly. Just looking at the rotation and considering what is happening, very peculiar things with that rotation occurs here. So if the frequency of applying rotating magnetic field is very low, so magnetic rod keep following that field in a synchronous rotation mode. So forming the vector of magnetic field and vector of magnetization form the constant angle after saturation. And all of a sudden, if you increase the frequency, so these two vectors, the magnetic rod cannot keep in pace with applied magnetic field, and you observe a synchronous rotation. And what is attractive from the experimental point of view, that you can detect that there is a demarcation between the synchronous and asynchronous rotations. You can detect that, and that is well-defined parameter associated with viscosity of the fluid. So that is what you can measure. So this is the illustration of possible reaching. So synchronous rotation, you see that the rod just keep in pace with applied magnetic field. Definitely you cannot see magnetic field, but you can measure it independently. In a second I'll show you how to do that. And that all of a sudden, the nanorod start to tumble, start to rotate, keeping the revolution, and then stop down. So now we need to put the relation between the frequency of applied magnetic field and measure the frequency of the nanorod rotation, and we will see a very nice peak. So that is where your spectroscopy comes into play. So basically you measure that, and we did that with different materials. Now, how to apply that that idea in practice? So now the most important thing is to eliminate the ambient biased magnetic field. So what we did, we put the fifth coil to play around to eliminate four coils are needed in order to apply in-plane magnetic field. The fifth coil can eliminate the ambient magnetic field. So actually, as you see here, the ambient magnetic field is not zero. Then you can cancel it out. So, and this is an example. I'll show a couple of examples of what you can do with magnetic rotation spectroscopy. A nanoliter drop of butterfly saliva, you can analyze in full that, and you can make a discovery that actually viscosity of saliva is comparable with the viscosity of the food butterflies typically use in a diet. More complex stories about the rheology of the blood of that insect. Again, the challenge here is the amount of liquid available. So we made the gentle surgical operation on moth, and I don't know, can I click on the movie? So you'll see. See if we can restart it. See? Okay. So I'm sure moving. You know, you'll see how it works. So for adult butterflies, you can measure viscosity. It changes depending on the way how butterflies drink. The butterflies visiting flowers, they have low viscosity compared to the hovering butterfly. The most challenging thing, and this is I wanted to show the movie, so is to look what happens with the blood full of cells. So here you will see the clamping of the cells, but you don't see it. Probably the mouse. If you could click it. So yes, you can observe that the cells are clamping and the nanorods are sitting between them. But looking at the way how that nanorod is hinged to the cells, and look what is happening here. Can you run down? Yep. So it seems impossible to learn anything about. But carefully analyzing the movie, what you'll see that actually, first of all, it's dilemma either to use Maxwell model or Kelvin model, because you don't know what exactly the material is. So the first idea, okay, these magnetic nanorods are sticking out from the cell aggregate, so they would experience the friction from the liquid around. So the first impression, it should be Maxwell type model explaining the thing, but it appears after the careful analysis of images, you will see that actually you can follow the major axis of that magnetic probe and analyze that actually that probe doesn't do any swing out of its normal position. So, and looking at the envelope, Pavel did a great job on filtering out the signal. You can actually distinguish between Maxwell and Kelvin model and say that most likely the aggregate behavior is a Kelvin model, meaning that you have a matrix resisting rotation of the material. So there is no emptiness, there is no simple plasma reacting on the magnetic probe, but mostly because of that reaction. So that is a summary of what I had, and the very last movie I wanted to show you, we started collaborating with Andrejs in 90s. I just graduated and I wanted to change the field, and read the paper Andrejs wrote about this assembly of magnetic nanorods. So I wanted to talk about that. I opened up that paper. To be honest, right now it's very hard even for me but to go back and see this. But this is a real thing. So and this is a very interesting sculpture bumped in Vatican Museum, and you can see that this kind of cluster appears all the time when you are working with magnetic nanorods. So you see they are coming together, they are forming very nice swarms, and if you play them in magnetic field, they are all. Okay, thank you very much, and I'm very excited to celebrate that great day with you. Thanks.
I had some questions myself, but in order to save a bit of time, we keep it for coffee break. So let's thank Professor Konja once again. And the next speaker is from the University of Latvia, Professor Ērglis, to talk about team science.
First of all, good afternoon, and I'm big like White Sparrow here, and so distinguished physicist audience, and I'm a doctor, but medical doctor I mean, and physician, but I really maybe try to beat in this. It's a big honor for me. I'm a bit nervous, and I actually want to show maybe what we are doing, how it's going in connections with physics. And when I see these very nice pictures of flowers and butterflies, then I remember always my teacher, physics teacher in first gymnasium, who says physics and lyrics is the same practically, and I'm also very honored to be here and in so great event like 70 birthdays, I mean celebration. And maybe I was a bit wrong, because actually we do so many things together with Andrejs and also with his team, and I'm really learn again very much. But on the other hand, I want maybe a bit to show how medicine is going together with other sciences, and that's what I like the Paul's comment very much. And actually I'm connecting also with physics, like my cousin is physicist in States too, and then we are sometimes spending hours to discuss the different kind of problems, and I really can learn from this. And this is always this disclosure slide. But actually, if you look on atherosclerosis or on disease, then you always see in each, and this is also what I always call for my students and also co-workers. It's also a butterfly. You should let to fly to the vessel. And there is so many substances, and you talk in different, but we talk in different scales sometimes. And that is why it is so important to put us together, actually, and really to understand what we want to do. And actually, if you look here, there's so many things, it's so difficult to say where is the risk and where is the disease. And actually, also, each this segment we can split and to look on from different kinds, from specialties, from chemistry, from biology, from physics, and so on. And that's why it is, I guess, so interesting. And at the end of the day, we are getting this eclair cake here, and this is what we need, what we should avoid. And because if this ruptures, then it's happened something which is not very good for us. I really want to show maybe a very example what I really was in last 30 years, I'd say, when I started like physician, and there was also always was the question who is the biggest and how we look and what is the main problem. Is it it's always the competition between surgeons and cardiologists, and of course it's not always the biggest dog is the most friendliest. And what's other, but this is always was competition. And for example, if we look on history of myocardial revascularization, then we see it's went parallelly. It's went by cardiologists, and also it was done by surgeons who did the bypasses, and we opened the vessels, and all disciplines really improve, but the competition never stopping, and even in last decade. But then once actually we met together and we really made a study, and as you see, this is of course, if we are looking on evidence-based medicine, we should really look on big data. Actually, this is the other question, and maybe I know that some people are saying that the big data is maybe nothing, but again, it doesn't matter, but we are looking on really big scale of studies, and as you see here, this is how we participate, and this was a competition, real randomized competition between surgery and cardiology. And actually it's only a method, it is not why what is so maybe important to go very deep in this. But then actually in the end of the day we really to find out groups where is a better surgery, where is a group better cardiology, and then we also find that what we need to do, we need to go for a heart team. And actually what we need to do, we need to really to be together and know the question who is more important. And it was not easy. It was not easy, and especially in the States. And then even now, it's because it's like it's always where the people, the cardiologists, was physicians. But for example, in UK and in Australia, the States was sir, and this is and then it's really was some problem. But what is very interesting that, as I said, by this heart team, we very much change guidelines. And this is so important. And again, what I want only with this to illustrate it, that this is a hard team, or it is a team, and only in team, from different disciplines, we can really to find a best solution. And as you see here, then we at that time, it was in somewhere in the end of 2007, 2008, was really we defined this heart team, and that now it's across the world it's working quite good. And as you see, it's even then came not only cardiologists, surgeons, invasive cardiologists, but also nephrologists and geriatricians and rehabilitation specialists, neurologists, diabetologists, anesthesiologists, so on, other specialists. And then once one woman came and asked, why there is not dentists? And I said, yeah, right. And also dentists should be there. And then, if we are looking even more, then we will see, and after your presentations, I see so important is also to, in this team, put inside biologists, physicists, chemistry and other specialists. And this is the way how we should go. And this is one of the examples. It's some 10 years old pictures. Everything is all pictures practically from Riga. And we started with valve transplantation, but it is groin arterial then we really how we says look on one target. This is like and cardiologists and surgeons, and this is a way how we. This is now it's a very usual procedure, but of course in past it was a bit more. It looks very fantastic, but now it's really easy to even to change by growing artery to valve, at least aortic. And that's why we started also to look more on team science, and I hope so that also in university, actually this is very good for Latvia, and as I said before, I unfortunately didn't put the pictures, what we did with Andrejs together, but actually we learned a lot, and now we have maybe not directly with this what we did, but in some sideways we find a very interesting things what we really can do with cells, and we have experimental work on this, but it's very good for Latvia that we are so close together, and as you see, this is a team science initiatives and designed to promote collaborative and often cross-disciplinary, and this is the most important point, cross-disciplinary approaches to analyzing research questions about particular phenomena. And that's what I'm really also to try to push, and I hope so that we will go for this more and more, and this is the way how we can really to find a new ways. And as you see, this transdisciplinarity is an integrative process in which research work jointly to develop and use a shared conceptual framework that synthesizes and extends discipline-specific theories, concepts, methods, or all three, to create new models and language to address a common research problem. And actually, yesterday I did a call that I was in Germany and then France, and this is what we discussed inside our, European Union cardiologist this network, and we see that we need to find a new languages if we really want to describe what we are really doing. And as I see, this is how we can expand this heart team and the clinical sciences, biology, anatomy, the mathematics and physics and biostatistics and computer sciences, engineering, animation and design, public health, epidemiology and social and behavioral sciences. And this is all this continuum what we are really need to work. And it's our everyday. That's what we are doing. What we are doing, we use ultrasound, and we are we are really good in imaging, and we really do. We also call up for ultrasound. But if you look at ultrasound and how we measure this, if everyone from you will laugh about that, because there is 1 millimeter is nothing, And then it's again the question: do we really understand exactly what we are doing? And that's again. It's not only about intravascular ultrasound, about optical coherence tomography. And actually, as you see, this is coming how it came from experimental model now to what we do every day. And this is coming from Cleveland Clinic. And when I see that in lab, and that was impressed me very much. That was very good friends my working, and it is online how Ērglis developing. Online thing, and then you can see every structure how it goes, and of course then for us that's how we can make a hypothesis what we should do and how we should go. Of course all mostly who did the revolutions in medicine, this is a physicist and as you showed before, who showed these fantastic pictures, and engineers. And this is but again, this is what we do is, for me, the shear stress is the main topic, but of course in which level. The cells are one of the main topics, but in which level, and how we can really to understand this. And this is one of this work what we did also together with Christoph Zarins from Stanford, and Charlie Taylor, and he's an engineer and also physicist, and it was based on computational fluid dynamics and quantified fluid pressure and velocity based on physical laws of mass conservation and momentum balance. And this is now actually we proved this in Riga, clinical part we did in Riga, and this is a very interesting how it's now going and actually now it's even in NICE and other guidelines accept that we can do, and actually what we, the clinical implication is that we can really to measure to not only anatomical things here in coronary vessels, but by angiography, by computer angiography, which is a static, we really can by program can to understand. I will finish in next 1 minute. Yeah, we really can understand the pressures and the functional significance. And this is only an example, and as you see, of course, it's also it's actually done. This picture by the same guys who did Jurassic Park, this animation, but it is what we're having now on iPads. This is the way how we are looking on medicine now. And of course, it is not the last call because we are not counting the cells here. And this is, again, I got so many ideas, even from this conference, and that's why I'm so honored to be here. But this is in reality how we can transfer this basic knowledges to clinic. And this is a way how we can measure what would be happen if we would put one or other stent. That's actually this is operating planner and so on. And this is what we need. We need to go from evidence-based medicine to personalized and translation medicine, and then from translation medicine actually to precision medicine. And precision medicine, this is again, this is quite interesting. It is something new. Maybe we don't understand exactly what this is, but at least this is describing individuals. Biology, clinical research, laboratory tests, including molecular and omics data, what we also mentioned, imaging findings and electronic health records. And this is about question about artificial intelligence. It's question how artificial intelligence can help natural intelligence and vice versa. And I think this is a very, very interesting, and that's why we have so many things now together. And the next time I will show how we uploaded cells together with magnetic things and others. And like to say, I got just approval today that how it's called, to approve our project, and this was the project will be about gene data lake project. And of course, it is a question how we can go and to look on bright future. But I really think that it will be. And thank you very much, Andrejs, always for your support, always pushing us. We are now very close, hospital and here, but now you will move next year, and I will go now a bit because I should go also to Ērglis, but I guess that we will meet there even more often. And actually, I also think that we can even to collaborate in our. And this is a picture, but all pictures are some of details, but each detail also have the details. We should not lose the picture, but of course we need to understand the details. Thank you very much.
Do we have time for one quick question? Is there any question from the audience? So please. Then okay, let's save a bit of time to catch the coffee break, and let's thank Professor Ērglis. I welcome the next speaker. It's Oļģerts Dumbrājs from the Institute of Solid State Physics. Andrejs is turning. Please.
Okay, I realized just now that the title of my talk is misleading. I'm going to talk about not strong magnets, but large, huge magnets. That is a bit different. But let me start with a very sad story. Because that... Yes, look, we know Maxwell equations, and we should remember that they are asymmetric. because magnetic monopoles, no one has found them, but no one has a theory which should say, well, they do not exist. So why I'm showing this slide? Because when I was young, I started my career as a particle physicist. And look what I wrote 50 years ago, that magnetic monopole is an unsolved problem in physics. Unfortunately, now I'm old, and after 50 years, I can repeat the same. And maybe some young people in the audience will just experience the discovery of magnetic monopole. Okay, but now to business-like conversation. Well, these huge magnets, they are related to fusion, and there are two methods of nuclear energy. The one is fusion, when the tiny nuclei, they fuse together, and this is called fusion. And the second one is fission. And all the nuclear power stations which exist until now, which work, they are fission. And that is atomic bomb fission, and we know it's very dangerous. On the other hand, fusion is the energy, fusion energy is just the energy of the sun, the energy, fusion. And just people now are working already for 50 years on tokamaks and stellarators. And these are the future fusion machines. And there are two problems. First of all, you see in the fusion, the positively charged particles, ions, they collide. And in order to get a fusion, one has to overcome the repulsive electric force. And then that means you have to accelerate ions, neutrons and helium and tritium. And this can be done by means, so this is fusion plasma, and one just injects, say, the electromagnetic energy, radio waves, and this is so-called plasma heating, current drive, and diagnostics. And this is done by means of gyrotrons. Now, what is a gyrotron? Look, this is very special tube, because one needs the frequency in the range of 170 gigahertz. And if you approach to this frequency from the left-hand side, say from klystrons, it doesn't work, because the mechanism, say in klystrons, everyone has nowadays at home microwave ovens, and there are inside magnetrons on klystrons. That mechanism doesn't work. On the other hand, if you come from high frequency side, from the side of lasers, it doesn't work either. Why? Because lasers are related to quantum mechanics, and the 1 millimeter, that is 1 or 2 millimeters, this is already no quantum mechanics. So many years ago, the gyron was invented. Now, what is the mechanism of the gyrotron? There is the gun, then there are magnets. Right, it doesn't work. Yes, you see superconducting magnets, and they are already large, but not so large. Now, what magnets are used in gyrotrons? First of all, permanent magnets, but the magnetic field is rather low, below 1 Tesla. Then there are water-cooled solenoids. The magnetic field is already around 1 Tesla, of frequency 28 gigahertz. Then there are superconducting solenoids, which produce magnetic field around 20 Tesla, or say 560 gigahertz. Then there are pulse solenoids, even higher frequency, higher magnetic fields, because this is, you see, this was formula, very simple one, that is cyclotron frequency, how it is related to magnetic field and to a relativistic factor. Okay. Now, this is how it works. The superconducting solenoid should be placed in a cryostat, and this is the typical scheme of such a magnet. This one, so I'm not going to dwell on this. Now, you see, the first gyrotron was tested in 1964 in Russia in the Gorky Institute. And the frequency was rather low, about 8 gigahertz. And nowadays, people work on gyrotrons for ether. I'm going now to tell you what is ether and what magnetic fields are there. But here I'm showing just gyrotron developed in Germany, in Karlsruhe, where I worked for many years, 15 years or even more. And so that is, so to say, gyrotrons. I am at home with gyrotrons, but not with magnets, rather with resonators. Now, this is the biggest experiment in the world nowadays, the so-called ITER, International Thermonuclear Experimental Reactor. This is the huge machine, and this is the largest tokamak in the world. And there are thousands and thousands of people working on this project. There is the United States, Russia, Korea, Japan, Europe as a whole, as a European Union, and it is situated in Catarache, that is southern France. Just to show you how large is this machine. It is, look, here is a man at this point. No, sorry, this is. So you can compare, say, this and with all that. Now, what is here? One has to confine the plasma in the tokamak. So the plasma is not allowed to touch the walls of the tokamak. So plasma is here, and then there are two magnetic fields. One is the longitudinal and toroidal magnetic field. And if you combine these fields, then the plasma is confined in this vessel and not touching the walls, and fusion reaction is going on. Now, just to show you how large is this machine, these are the fields which are needed for this tokamak, ether tokamak. That is the peak toroidal field is about 12 Tesla, then toroidal field on the axis 5 Tesla, and peak colloidal field on coil 6 Tesla. And the fusion power will be about 500 megawatts, and continuous operation about 1,000 seconds. And it was postponed, and originally it was planned that it will start to operate in the year 2000, and now the plans are maybe next year, but I don't believe maybe after 5 years or so. Just this is next to the last, my slide, but just few, such a joke, but again, sad joke about the fusion. Say if you, because there are many physicists who say that fusion will never work, and it goes such an anecdotic, if you ask fusion people, fusion physicists, when the fusion will work, they say after 20 years, and they are right, and they will answer all the time this way. So it is invariant. Okay, and now my last, that you see, this is my last slide. How huge is this? So 30 meters wide, 20 meters cryostat, 28, then the 1,250 tons, huge magnets, and again, where is this dia? I cannot see it. I think, again, so probably, oh, here, yes. So how huge is this machine? So this is, my story was during these 50 years. Look, we started with small magnets, and this is what we have now. Thank you.
We have time for one quick question. Is there any? If not, then let's thank Oļģerts Dumbrājs once again. And let's invite Professor Cēbers to give a talk on actually why we are here.
First of all, I am very thankful to everybody who attended our meeting. Thanks a lot. And during a short period of time, I would like to give some overview of my activities during these 50 years on magnetism. I have more failures than successes, but I will try to be positive and speak more about successes than about the failures. And the beginning, actually, of my activities in this field was already mentioned by Elmārs Blūms. It was around the 70s, and then the Laboratory of Heat and Mass Transfer were changing the subject of their research and looking on magnetohydrodynamics in broader sense, that it is some science which consider laws of behavior of different media under the action of electromagnetic fields. The principal question then, of course, was to which start, what are the forces which electromagnetic field acts on the media? And so I was inspired to look on this problem from point of view, maybe who knows, there is the tensor of energy and impulse, and which defines the force which acts on media and electromagnetic field. I got some understanding about the symmetry of this stress tensor and things like that. And then this period, in the laboratory, the viscosity of these magnetic fluids were measured, and somehow I had the idea that these viscosity measurements could give some, in some way are connected with the question of the symmetry of some stress tensor. And then I derived some, as far is still valid, some expression for irreversible production of the entropy, where some new term appeared. If you have magnetization, the particle rotates with angular velocity, then it will change this magnetization. And this term allows explain, for example, increase of viscosity in the field and things like that. And when I have derived this, I wrote some abstract. Elmārs said, you don't know how to write an abstract, I will rewrite it. While he was doing this, I have gone to the library, took the last number of Jet and have found this equation with this term just in the last issue of Jet. So it was the first failure, and this never has been published actually, but it was, I guess, error because it was even now it is more or less original. But connecting with this subject, it was my first real, how to say, joy connected with the physics. Very simple one, but from these all equations, I could derive that viscosity if you apply magnetic field to capillary perpendicularly to axis of capillary twice less than if you apply in longitudinal direction. Just was Zhenya Mozgova has measured in this experiment. And I was really happy to obtain this thing. Well, this idea about internal rotations continued to interest me for many years and even till now. And the one which I would like maybe to mention, I have considered what will happen with the conductivity of liquid if you add to this liquid some, let us say, particles which are not conductive. But these particles could rotate and And by rotation, they can transfer the charge which is accumulated on the surface of the particles. And the derivation predicted that if even you add non-conductive particles to the liquid, due to these rotational particles, conductivity can increase. And later years, this actually maybe one of some theoretical prediction indeed were confirmed experimentally. And this is also one good thing. Namely, in these years, I derived some particular model, now not with magnetic fields, but there is some analogies of liquid with polarization, where some special equation for polarization taking into account that the particles rotate were derived exactly from equations of electrostatics and Ohm's law. And it was applied at first to the problem of the motion of ion in polarizable liquid and could predict that the effective friction for ion motion due to this relaxation process which is incorporated here increases. And also at the same time Larsson Zager wrote his last paper on namely this problem and in some numerical, he has done of course much more than me, but the numbers were the same. And equations I just showed you here, actually it was done in 1980, and these equations as it turned out later are exactly equivalent to the famous Lorentz equations. But at that period I never knew that if I could use that, these Lorentz equations, then maybe it would cause some resonance at that time. But some of the predictions about the behavior of some non-conductive particles in liquids with low conductivity were predicted. There's some chaos phenomena for these particles, and later some predictions for example, that in some intermediate range of electric fields, the two states for elongated particle is possible. One oriented along electric field, another one which is perpendicular to electric field but rotates. And some last year, just this prediction was found also experimentally. Period after some 2 or 3 years after PhD, for me actually was the most fruitful. I have derived equations I shown just a moment. Also, we found or even discovered new kind of instability of magnetic liquids in thin Helle-Shaw films. Here is some droplet between two plates. Field is out of the plane, and if you increase it, increase the field, it is unstable. Some non-axisymmetric shapes are developed. I understood one moment looking on some experimental photos when people have published in the journal. I could not understand why they observed such a strange figures of shapes of the droplets, and I understood that something is connected with the stability of the circular shape. And when it was understood, all further things was already more or less simple. And then some kind of a bit joke. Somehow I derived a theorem that the bubble in infinite layer of magnetic liquid should behave in the same way as the magnetic liquid droplet surrounded by non-magnetic liquid. And I asked Misha Mayorov that we should check this theorem. So he made some circular Helle-Shaw cell, glued the perimeter, and made only one hole. And with the start to introduce magnetic liquid through this hole, but pressure increased, and we could get only a bit magnetic liquid around and big bubble in the center, which of course is not what I wanted. I wanted one small bubble surrounded by a large amount of liquid. And what to do? And we continued with this large bubble and called very beautiful phenomena that there are some critical magnetic fields, some figures are arising, they still grow as you increase the field, and finally we get the labyrinthine pattern. This is, I guess, very important work which he done. My friend says that if you sell something good, it will cause something else very good. And even this subject of this labyrinthine pattern formation has produced a lot of good things. One of the things was it could be predicted, for example, that equilibrium periodic structure of magnetic stripes can have negative surface tension, effective negative surface tension. And my French colleagues, it was checked experimentally, and there is shown how from this stripe pattern we can get some chevron pattern. This kind of subjects could be applied also to different systems. Here is completely different system. It is to the field of spintronics, where you have ferromagnetic material, some non-homogeneous current is going out, and current carries also spin of electron, which interacts with the spins on the lattice, which gives rise to ferromagnetism, so you can move the domain walls, and if the direction of the current is in right way, you have again some kind of instabilities which we show together. That is a completely different system. Besides this, at that period, we have developed very nice mathematics how to simulate this pattern formation. This was my simulation, the first one, when I, from some circular drop, got some bundle as seen in experiment. And at this moment, I again was very happy when I draw numerical results by hand on, how to say in English, millimeter paper. It was not possible then to make a pictures on computer. And this kind of mathematical technique was very good one. Later, just last year, by this technique of boundary integral equations, it was possible in some way to calculate numerically the shapes of the droplets, very magnetic droplets in rotating magnetic field, where these droplets undergo a set of bifurcations, circular, elongated circle, and then back to circular pancake again. And last year, there are experimental data of Gunter's Kittenberg from this kind of instability, and here is numerical simulation by Jānis Ērglis of this kind of droplets. And what is this? And in the same years, around 1980s, that is several years after PhD thesis, I think that is still valid even nowadays. It was a prediction that if you have some colloid of magnetic particles, you can cause condensation, or better say, the mixing by increasing magnetic field. And here is corresponding curves. Between these solid curves, there is the mixing. That means you increase magnetic field at given concentration, go in this region, and then you cause phase separation, and from particles, magnetic particles start to condense. And this is a bit joke, but it has never actually been more or less published, but the joke was how I get a great respect from French people. They were doing some experiments on spike formation on the ferrofluid surface, and I entered in the lab when they had 9 spikes on the border of the Petri dish where the magnetic liquid was put on. And I said, the next one will come in the center. It came. Then I said, the next will come in the neighbor of the first one. It came. It continued till 18, when there were 2 layers of these spikes, 5 in the center, or 13 around, and I said that the 19 will come in the center of these 5, and it came. And from this time, I got a very great respect from French people, only we never established this, of course. And now, in the last years, we also, with my team, worked a lot on the behavior of different magnetic flexible structures. Here is one. Where is my mouse? My mouse is disappearing. And here is one example. This is a flexible magnetic rod, and which is magnetic, ferromagnetic. Your inverse magnetic field, it makes loop, and so third dimension it relaxes to the new direction of the magnetic field. The same, it is numerics, but the same thing was seen by Kasper's experiment. And another example, just we were doing a lot of different magnetic streamers. Here is again the same magnetic filament, but in AC magnetic field, it buckles, straighten out, buckles, straighten out, and by this it moves forward. So this is some subject of us now. And another subject in which we are interested are magnetic bacteria. Here is the simplest example, which we have published in the paper together with Paul and his colleagues. Magnetic bacteria, rotating magnetic field moves in the circle. Afterwards, there's some other interesting things happening, and we still continue to work on that. And that is the last one, which we do now. A lot of these bacteria, which now are in so-called asynchronous regime, which Kornev has mentioned, and so they attract each other due to the high dynamic interaction, because they are in the liquid. They make some swarm, and then suddenly from this swarm arise some doublets of synchronized bacteria moving together, which leaves this aggregate. And this a bit reminds me of this next slide is for Andrejs Cēbers, but this one is a sort of famous game of life. When some periodic structures start to emit gliders, it remains this. And now I wanted to show one just slide, especially maybe for Andrejs Ērglis, to remind about some ideas which we had some time ago, but this is not that. Just a moment. Yes. We had some idea that it will be nice to make some magnetic stem cells. Right. Even we got some dirty thing which reacted on the magnetic field. We only did not know where these magnetic particles are. And Kaspar shown one issue, quite recent I think, of New Scientist, where the British guys have put magnetic particles on the stem cells and say that is a good thing. Yeah, so we should continue this thing. Yes, thank you.
The floor is open for questions and comments. I know there is at least one. Yes. Any questions? Quick questions? I guess we'll have plenty for the coffee break, but there is one comment at least coming. Please, Professor Cēbers.
So I have a very important mission from and on behalf of the Academy of Science, of its leadership, to deliver this very important honorary mention, yes, you'll see now how beautiful it is, number 134, for the member of the Academy, Andrejs Cēbers, par nozīmīgu ieguldījumu magnetohidrodinamikas attīstībā Latvijā. I guess everybody understood. And it is signed by the president of the Academy himself, Mr. Sparitis, and also by the Senate chair, Jānis Stradiņš. So, this is I know about small disagreement between Professor Cēbers and Professor Ērglis about the smoking. Is it a risk factor, or it might be even positive for some achievements that cause? But on this special, not very special, very special paper, everybody will agree that it may have only the positive.
Anyone else, or we close the session? I guess we close the session and we continue with a coffee break, and we come back at 4:15. Turpināt četros 15. Paldies.